Are you able to hear me now?
Yes, sir. Yes, sir.
Okay, sorry for the delay. I think there was some confusion in muting. Good evening, one and all. It's a pleasure to me be here talking about this subject. See, I think human machine interface is something not very new, right? It's already in practice around the world. So probably this session could be a foundation for understanding various type of human machine interface that is in practice and how it is taking shape world over in industrial scenario. That's the way we are going to deal it. See, basically, we'll try to understand what is HMI is all about, and what is the growth driver for such a market, and what is the kind of opportunities that is available around the world. And the technology part, frankly, no, today's session we will not have time really to get into technology. That's not the intention also. But however, being from the industry side, I will try to give you some examples, some videos of HMIs that is being used in a advanced level. Okay. With that short introduction, let me jump because already we have lost 10 minutes. So I like to get into the subject straight away. So I think since there is a video now, I'm because of the time now, I'm just cutting short. I'm from TVS Sensing Solution. This company was a joint venture between TVS and Cherry Corporation US initially for the first 10 years. Then it had a joint venture with a German company called ZF, which is the automotive major. And in 2018 onwards, we have bought back all the shares and we have become 100% TVS. In this company, we are really designing and mass producing switches, sensors, solenoids, and electronic component carriers or insert molded components. And recently, we also embarked on a journey into EV products. And we are also having an innovation lab, uh, which is engaged in embedded systems and connected products. That's a kind of short introduction about the organization which I belong to. So today's topic of HMI, we'll try to deal in kind of five ways. I don't think I will just to switch off my video because I want you to more focus on the presentation. Whenever it is necessary, I'll come on video again and I can take the questions. So basically, we'll take this whole subject into kind of five phases. First is how HMI has evolved over the period and what are the principles and components of HMC and the collaboration of HM interaction in real world. We'll also look into some case studies now to give you how it is being used in industry and what are the future work that is possible. And of course, what are the benefits and limitations of this HMI technology. That's the way we will deal today, the HMI subject. So, if you start from scratch, on a white paper, how this HMI was initially in the world, if you take a kind of human evolution, I think everything started with physical work, right? Then slowly for reducing the effort versus no result, increasing the effort versus the result ratio, people have started employing different techniques. A machine that reduces physical labor effort is designed to minimize physical strain on human workers. That's the way the first generation evolution has happened. The second generation, I think lot of buttons which has come into play, like machine that displays data or information and present the results in human readable formats. So whatever you see in the screen, probably some of us would have seen, and I'm not sure in this generation, many of the people would not have even seen this kind of machines. This is a second generation evolution on the human machine interface. Then came the advent of computers that provides output with feedback and designed to perform task while continuously monitoring its performance. Okay, that is the way all these machines know what you see in the screen, whether it is the first generation computer or air conditioning or washing machines or the TVs. These are the things now which came into picture. Fourth generation, where we are very familiar with the machines with computing power, is any system that processes, analyzes, and manipulates data to perform very specific tasks, solve problems, and make decisions. I think I need not explain too much on this. We are all very familiar with this area. Then comes the fifth generation, where intelligent machines are system designed to mimic human-like cognitive functions. I think this is the era where we belong to now. Slowly, things are now taken over by more robotics, automation, AI, such kind of things, right? So we are seeing that already, glimpses of them already coming into practices. To understand human machine interface market, you can see this data now, which is given the market size and market dynamics and ecosystem. There are some established surveys which are giving with a CAGR of 4.8% and market size worth from 2.5 billion by 2032. That's a kind of this is a kind of latest data, no, maybe 3-4 months old. Um, uh, so that shows a kind of now good growth potential that is available. You can also see some numbers in the related area. For example, the IoT solutions poses something like 1.29 trillion dollar worth of revenues, predicted, given by the IDC. Some of the insights, which is given by Lakshmi Gaga by 13th April 2024, 2.7 billion projected market by 2032, which we discussed, and 1.6 billion last year, and in midway 2028 it is predicted to become 7.7 billion dollars in global market. So annual CAGR in the first phase between 23 to 28 is supposed to be something like 8.2%. So increasing adoption of automation technologies enhance productivity and efficiency in manufacturing and focus on real-time data visualization. I think more and more gone are the days where the data is generated separately, then analytics happen on offline. Then by the time we take decisions, we would have lost some of the productivity. Now, no more it is so. I think the whole world is moving on to real-time data collection as well as analysis of the data as well as coming to decisions. That's the way the industry is moving. So this is the kind of we so far discussed about what is HMI is all about and what is the kind of market that is available for this between now and 2032. Then it is part of I would say in somewhere it is connected with the IoT. That's the reason I talked about 2 trillion plus dollar opportunity that is available in this area, which HME is part of it. And we also talked about how human effort is lessened with the more and more human machine interface that's happening. And very recently, this is also taken over by more and more by robotical control with the AI inducted, so that I think majority of the efforts, which wherever it is repetitive nature, that's all now replaced by this kind of collaboration with the machines. Now we'll see what are the components and principles of HMC. This is a framework. The loop highlights the continuous human-machine interaction, enabling efficient task-oriented execution, commonly used in automation, robotics, and human computer interaction. See, you can you must be knowing already. Any computer is nothing but it's mimicking human brain. That's the way things are. There is a kind of sensing, there is a information processing, and there is a control. So whatever our human brain works, the same thing we are trying to mimic by the way of developing machines, which also does that. And more uh, repetitive nature of jobs are getting replaced by machines instead of humans doing that, so that those efforts can be saved for doing a better job by the humans. The components of human machine interface has been shown here. I think it gives a kind of huge data work. You can see that there is a, it is called, the entire system is called cyber physical system, CPS, or some people call it as a kind of smart system. It could be a smart factory or it could be a smart grid. Um, Whatever, no, we just have affix the name smart, then it becomes a cyber physical system. So there is a perception, then there is a cognitive systems that take over, and there is a interaction that is happening. So what are the physical things involved through motion sensor, health monitoring sensors, wearable sensors, environmental sensors, all variety of sensors. Now what you see on the left hand side with blue colors, these are all the things which are really taking the data inputs. Okay, then whatever data comes out of that, or these sensors are sensing something and creating signals. These are interpreted by the cognitive system like machine learning, planning and scheduling, optimization, algorithms, knowledge representation, cognitive computing, simulation, big data, virtual reality, VR, computer vision, and a recommender system. All these things are on the cognitive part that's happening, the second part of it. The third one is actually kind of execution that's happening. Collaborative robots, which are called cobots, and exoskeletons, augmented reality, human machine interface, HMI, which we are looking at, and social networks, teleoperator system, and digital design. These are the things, no. So putting together the perception stage, cognitive systems, and interaction, all these three put together, it's called cyber physical system environment. What are the principles of human machine collaboration? Number one, there are shared goals, alignment of human and machine objectives. See, if you consider the manufacturing environment, for example, if you have to know, just imagine a manufacturing environment. Uh, 2 decades back, no, everything almost, especially countries like India, it's all manual. All the assemblies and other things have happened manually. Slowly, we started having instruments that can make probably it's a trouble-free assembly manufacturing. This can be called as jigs and fixes, poke-case, and all such kind of things. No, those things have happened. And then because of the productivity requirements, semi-automation came into place wherever the process is going to be of repetitive nature, then probably it can have kind of machine intervention. So, but when we are going for human-machine collaboration, number one is whatever humans were doing at some point of time, that is being done by the machines. Okay, so there should be a perfect understanding between what we want to achieve as a human. This same kind of thing, that goal should be similar for the machine also. That's what we call it as alignment of human and machine objectives. Clear goals, shared goal is number one. Clear goals, defining areas of expertise for humans and machines. When we are calling it as human-machine collaboration, we are not talking about 100% robotics, means no manless operation. We are talking about operations where humans and machines are existing collaboratively. So in such cases, there should be very clear demarcation of what a human being is going to do and what the machine will do. Okay, so what are the products that is going to be manufactured? Within that, what are the process available? in which process have to be really carried out by robots, and which processes probably carried out by human beings. That clarity should emerge. Adaptability, flexibility to adjust to changing environments, that is also very important. And transparency, understanding machine decision making process, no, that has to be very clear. If these are the basic principles that has to be tested before we are getting into or designing a proper HMI. So in the second portion of, we are trying to understand what is HMI today. We talked about the evolution of HMI, starting from kind of human work, and how uh, um, in the earlier part of machines came in, which are even in whatever today we are having all smartphones, touch phones. I think it all started with button phones, right? You would have seen the button phones, and from there only it got changed now, and we are having smartphones in hand today. And in future, uh, this can be much more automated than what we are seeing today. This is on the evaluation portion. And on the components and principle portion, what are the most important components? We talked about cyber physical systems, and cyber physical system talks about first sensing, which is called a perception phase, which is carried out through sensors. Then there is a kind of analytics and other things that are happening. The third one is the intervention by way of either HMI or cobots, those kind of things. Okay. And what are the basic principle for HMI also, we have seen how the goals should be shared, and it should be transparent, and there should be a kind of alignment. That is very important. With this understanding, let us get into the collaboration of human machine interaction in real world. But I think it's very simple, because this subject, as I said, is not a kind of rocket science. It is already into existence, and many of them we are going through knowingly or unknowingly in our daily life. That's the advantage. So it is very easy to understand. So let us take some examples for us to understand it more better. So how this collaboration of human machine interaction is happening? Let us take in society. There are human interactive devices. By seeing the picture itself, now you can understand what we are talking about. And there are innovative devices which is used in the medical field. You can see here how things can be, the X-rays, and it's a kind of handheld X-ray, which is happening. And transformed living. So the in the data world now today, I think many things are available. Starting from you take a ATM. This is in a way, it's a kind of HMI, right? What we are using. Previously, you have to go to a bank, step in, you have to go through a procedure, process. Lot of manual intervention is required before you take a cash in or deposit. But today, everything is that kind of say, touch screen, not even button. Now it's touch screen. So within few minutes, now you are in a position now really to have whatever you want. In the banking operation is completely getting automated. It's almost becoming kind of manless, except we have any problems, there is a grievance addressal, then you have to go to the bank. Otherwise, you need not step into the bank. Okay. Similarly, you need to have physical cash, and go anywhere you go, you have to carry cash and other things. Today, everything's got replaced. Previously, this is all today. We are using many cards, right? Credit cards, debit cards, those kind of things. Now, like GPay and other things have come into picture with our smart devices. So I think our life is completely transformed in the last 1 decade by having many things. How the way we interact with the society, it has gone through a very big change. Okay. If you take in industry the same way, healthcare industry is something now where I think HMI is invaded very deeply, and robotic surgery for precision healthcare is happening. AI assisted diagnostic is happening. Autonomous vehicles are being used everywhere. You called AGVs and other things are there, and soon they will be on the road also, right? Already people have started seeing it. The glimpses of that is happening already. Education again, where a lot of virtual assistants are today available in education. The way the education was carried out, learning process was carried out, it has gone through a tremendous change with this kind of human machine interface. So these are some of the things which giving a clarity for you to think. All these things are you are already using or already you've seen it. Only to bring focus on what are the HMI today we are using it. No, smartwatch is, I think this has become kind of hygiene factor today. No, everybody today. I think this morning, for example, in our factory, we brought a kind of health initiative wherein we decided that people have to walk at least 7,000 steps per day. So how to achieve that? No, so we decided we have created a platform in which everybody can log in, and either through with the app, they can step up the app. We can either through our phone or smartwatch, we can really gauge how many steps we are walking in a daily basis, and it also gives kind of min max average and who has done kind of pretty well and consistency. All these things are being done. And smart glass again, VR headsets, virtual reality headsets. These are all the things which have come into play already. Human interaction devices widely used in society, blending technology with daily life to enhance connectivity, productivity, and VR kind of thing is all for immersive experience. Frankly, no, without car driving, for example, you today it's possible for you to sit in a kind of a chair and understand the driving completely. You can do the racing by sitting with this kind of virtual reality headsets. Gaming, a lot many places now these immersive experiences are being used. Smart transportation. You can see here. No more the gone are the days now where human beings control the traffic. No more it is possible because of the kind of population of both human beings as well as the vehicles. So there are a lot of smart systems which are required really to sense this kind of vehicle, how they are moving, and how they can be really channelized and controlled. So that's a part of smart transportation. Simulators, ADAS real world driving. I was just giving this example in the previous slide. It's possible for us to completely understand our driving through simulators. Simulators are available even for flights. It's usual handling flights as you are in the air. Similar, you can also be in the simulators for understanding all risky challenges that you might go through when you are going to handle flights. Autonomous vehicle driverless car. I think this is a kind of very hot topic which is going around the world. Every leading car manufacturers hopes so that at one point of time they will have this kind of autonomous vehicle. Some time back, I think Google car you would have seen everywhere. It is on the media. So human machine collaboration in transportation includes autonomous vehicles, autonomous driver assistance systems, which is called ADAS, and a smart traffic management solution. Today, if you take any mid-size to high-end cars, you'll be seeing already ADAS systems that are available at various levels, including it has collision control between one car to another car. It is also able to sense the speed of the car which we are following. If there is a kind of any issue happening with that, there could be a kind of braking that can be applied in our car also for avoiding any kind of damages that can happen or fatal accidents that can happen. Smart rings. right? It's all kind of fitness tracking, sleep monitoring. I think huge evolution has happened in terms of in the fitness area and health monitoring area with the lot of it's all called wearables, right? These wearables actually sense the condition monitoring of our physical health, and it tracks many parameters. It could be your blood pressure, sugar, heartbeat, right? All those things. Actually, if you start talking on only one this topic on medical field, there are many appliances that are available today that can help maintaining your health as well as the longevity procedures. Vending machines, for example, no, instead of having a kind of vendor sitting and physically selling things today at kind of you can select. These are all available in the airports and railway stations and malls and whatnot, and this is becoming a part of our daily life. Smartphones, I need not tell. I think world over, no, this has become something which cannot be ignored anymore. So innovative devices that integrate technology into everyday life, offering convenience, automation, and seamless communication for enhanced user experiences. Let us see some more. Already you see in Amazon, Google, this voice assistant that is happening. It's also available in the cars nowadays. It's possible for you to have them, these apps, and adaptive ATMs and home automation devices. Many automation devices. I think a majority of there is a saying that your kitchen, complete kitchen. Yesterday I saw a video. Uh, it can give anything, whatever it gives. It has kind of hundreds of recipes that is available. It also says what are the ingredients probably you have to put in. There is a weighing scale available in the instrument machine itself, where by putting all those ingredients on the quantity that is showing up on the screen, your complete cooking experience will become automated. That's the kind of thing that is happening. Already you would have seen that in big restaurants and other things, many of the things have been automated. Dosas, today you can print dosa, whatever size you want, you can print dosas. Those kind of things are coming into picture. So transform living spaces by enabling seamless control, automation, and interaction through voice commands and smart banking experience. I think majority of things so far what I talked about, I think we are having already going through this experience without thinking them as HMIs. We are going through them in our day-to-day life. I hope all of you agree with me. Medical imaging, huge changes happen with the advent of HMIs. Huge changes happen, and more and more they are also becoming portable. Previously, very complicated test equipments which are there, bulky, and you have to go to specific places. Now slowly they are all becoming portable, and it can go to the place where the patient is. That's the way it is becoming. And interactive anatomical display, you can see in the screen now what's happening. So in a way, education, when I said that education is transformed, you can imagine the way medical science it was there, or it was taught before a few decades ago. Compared to that, today I think even common man who is not having no real knowledge, he has access to so much of information about our own human anatomy and the kind of diseases what you can go through. People have gone to the level of understanding. They know the problem. They are also when they go to doctor, we go with whether it is good or bad. No, they go with the 50% plus knowledge of even selection of medicines. No, they go and suggest and start interacting. That's the way I think life has changed because of enormous information that is available. And surgical robot. This is some interesting area where the precision and accuracy and consistency is required. The robots are being used. And you can also understand the expertise in the medical field. No, sometimes it becomes scarce. Very, very complicated operations if they have to be made nowadays. No, it's possible for somebody from uh, either UK or New York. The gentleman can be in your operation theater giving commands through screen, so that no either the robo or doctors no can perform the surgery. That way, um, the society is getting access to the best possible services, medical services, that is getting enabled. So, cutting edge technologies are revolutionizing healthcare by providing very detailed visualizations, enhancing surgical precision. Teaching assistance robots are available. Uh, this is becoming more and more prevalent in some countries. And I think in India also you would have seen in media, no, like this kind of teaching assistance robots, no, they are coming to play. Virtual meeting, I think the whole world has learned that post COVID, I think the online thing has become a part of our life. Um, it has completely transformed the way the meetings happen, the way product developments have happened. Everything got changed with this kind of virtual tools that are available today. So today also we are also meeting now through virtual source. That is all done because of the technology advancement. So innovative technology is designed to enhance learning experience by providing very personalized guidance. Quality check augmented reality. So in the manufacturing, now you can see uh, haptics also have come into play. Where, for example, let us say, just I'm giving an example. If let us say some 800 parts have to be assembled for a engine, no, even for training a new person to get into a kind of assembly procedure, usually takes no time, like some years for him to master such kind of assembly. Whereas what's happening now with the advent of haptics, it's possible to train all possible assembly can be taught through this haptics, so that uh, the learning process is quick and as short as possible, so that you'll be in a position to understand without even going there. It is similar to what I was talking about some time back, driving. Even without going to roads, it is possible for you to have a simulator. Similar kind of things is possible. Haptics is again a kind of simulator which you can use it for learning the manufacturing process. Precision manufacturing, we can go with the accuracy levels as high as possible with the advent of robots. Robots can be used in many places. Uh, so there could be a question: why then everything cannot be automated? See, frankly, you have to think this way. We should not do the automation just for the sake of automation. Wherever humans are in danger to work somewhere, or wherever it is very transactional, so that it is very repetitive again and again, so that humans can become tired of conducting such kind of things. um, this kind of robots can be held there. And another thing is, in hazardous situations, let us say that there is a mining that has to happen. In the mining, if you have to access to some deeper places, I think robots can be used there to go there, so that they do not have this problem of if there is going to be a dangerous gas that is available inside the mine. No, so those kind of places, instead of exposing human life, it is possible to deploy these kind of machines. So transformative technologies that enhance industrial process, enabling a very collaborative work. Process and safety industry, you can see operator machine interface for a power plant. The entire process can be actually put on the screen. Completely, it can be all connected. Process control, you can see here. Similarly, every machine today you see in our shop floor also, I think every machine is having a HMI where you can interact many of, for example, even the any adjustments you want to do or failure modes, everything is menu driven, so that you will be able to quickly go and do that. For just to give you a very simple example, if there is a kind of molding machine with a HMI, the output you are seeing that the output also can be actually done by a vision system to know to check whether the product output is okay on the as per the control plan, no, whether everything is okay. And if at all by seeing that you are seeing there are some process that has to be adjusted, failure modes you are finding out in the rejection. So you can go into the HMI and today it's all menu driven. If you know already if these processes are so much stabilized, you know that there are 12 types of failure that can happen. Then these 12 are put on a kind of drop down menu, and the quality inspector will be select the most relevant one and click it, and so the rejection chute will open, and the rejection will be put there itself. So the analytics also can happen simultaneously with the human intervention. That's why we call it as HMI. It's not 100% automated, but human intelligence is also used. But repetitive jobs are where it is possible to, really deploy analytics through machines. No, those are all things that is carried out. Test rigs, the same similar kind of HMIs can be used. And later we'll see some videos we have used in even in our company. So safety systems, no, wherever if we have a kind of huge factory where vehicles are moving and there are alleys where they can come into collision. So there are systems today available to tell you that there is a vehicle that is coming on the way, so you have to stop. So you'll be seeing a kind of red light that is now beamed on the floor with stop lettering, so that people understand that they have to stop the machine, otherwise there is a possibility of accident. So create flexible, user-friendly production environments, ensuring efficient assembly process and seamless interaction between workers and machines. All these things are, as I said, there should be some basic principles for when you are doing HMIs. Majority of the places you can see that either they will be number one, it will be all visually controlled. Number two, safety aspects are taken care in a majority of the cases. Now, I think wherever safety is the most important thing, I think this kind of human machine interface is of no very great use. In the daily life, these are the, I would say, evolution of HMI that is happening. So ergonomics in headphone evolution efficiently focuses on optimizing people's comfort, usability, and safety. Okay. Previously, it used to be quite big, and slowly, you would have seen the phones and Walkman, and in here, headphone. Then earpods have come. Now earbuds with the touch control as we have started using it. So more and more, it is becoming more sophisticated and user friendly. Here again, it talks about how data input has happened. The evolution. First, Scholz and Didden typewriter, then mechanical typographer. All these things, I think many of you would not have even seen it. And Apple keyboard, the first generation keyboards, when they came, they used to be very bulky with large buttons. And today, all these things are getting replaced by more membrane and roll-up keyboards. The keyboards can why roll-up keyboard? Physical keyboards are even replaced with the laser ones now, which is coming as a light, so that you will be able to even typing. That's a kind of innovative designs that are coming up. So all these things are showing how the HMI has evolved from the scratch to where we are today. You see wired remote controls, reality remotes, how it used to be, it's all wired. Then infrared remotes have come into picture, then universal remotes. So you can use them with many appliances at one stroke. Then smart remotes with voice commands have started coming in, and app-based remotes are order of the day today. So ergonomics In remotes, improves ease of use and simplifies controlling multiple devices. See, this picture actually tells us when you say HMI, it has two things, right? Human and machine. Then there is an interface. In the past, how the HMI was, all the work has been carried out by humans, and the data was input again by humans into a system, and they used to do the kind of analysis. Currently, we have gone through many evaluation. Today, the shop floor is handled by both humans and robots. That's what you are seeing in this picture. Okay. And data is integrated through IoT systems and all, so that whatever is happening in the shop floor, it can come to system automatically, so that analytics can happen, and anything on need basis human intervention is happening. Okay, that's the way the current systems are. In future, this is going to be more of you can see that uh, humans in the current humans are having a kind of upper control over machines, and in future probably machines will have kind of better control over humans. That's the way they are going to tell in a very predictive way what are the options available, and what is the best option for that particular instance. Okay, that way robots will have kind of larger control over manufacturing systems, and the interactions are going to be way different from what it is in the past or current. So, from industrial tools to industrial robots, evolution of human machine collaboration, past manual effort, present shared innovation, and future seamless integration. That's what is going to happen. Okay. So, with this, I think we have seen how what is HMI, how it is evolved, what are the components and principles of HMI, and we have seen in detailed way how in society or in industry or medical field or banking how this collaboration of HMI interaction is happening, and we also saw a few examples of in each of that kind of adventure, whether it is a kind of remote or keyboard, how from the evolution has happened in different phases. That's what we see. So let us see now some case studies which probably would be of more interest to you. So I'm going to say two or three, depending on the time availability. No, I'm going to just show two or three case studies. So the case study one is Cobos in engine assembly line of Bajaj Auto. Why this is coming into picture is I think I was told that this is one of the first Cobos that came in India way back in 2010, if I'm right. This was put on their shop floor. The problem statement is more of repetition of multiple activity in assembly. More number of visual checks depend on man, and high chances of process skip, so failure modes, and high assembly skilled level operator dependency is there. If somebody is there, not there, who is a kind of skilled, then that particular job gets affected. Because of that, the dependent jobs also gets affected. Higher cycle time of process and organization, high risk occupation policy. So gender friendly handling of weights and etc. So the engine assembly line of Bajaj Auto has come up with the first cobots in the assembly line. Wherever this kind of repetitive jobs have been handled by robots, and they used to enable humans doing the core jobs. That's the way it has happened. Here comes one kind of interesting thing. Let us see this video. I hope the bandwidth is enough for you to see this video. I will try to put this. So hope this was interesting. Um, we are talking about repetitive jobs getting replaced, by these robots, but the entire thing is not automated. Rather, whatever is repetitive, it's automated, while humans, take care of where intelligence is required. That's the way. So both robots and humans were collaborating in the shop floor. That's why they are called the cobos. And the case study too, it's a cobot assembly line in our own factory. This is a kind of electrical actuator assembly wherein there are some leak and high voltage testing has to happen. The problem statement is previously it was all done manually. The product has to move from station to station manually, and high fatigue due to repeated actions and manual errors in assembly. Sometimes, no, one of the process, if it is missed out, then that will have a repercussions in the customer's place. So outputs were lower and high setting time. These are the problems that have been identified. So these leak testings have been we have now started using kind of human machine collaboration. You can see them in the video. So this is a kind of EOL tester finally that takes a, previously we used to have the problem of skipping one of those testing. If it happens, then it becomes a problem. Now with the application of these robots here, uh, we were able to get better productivity and consistency on output. Um, so that's the advantage what we got. We'll talk about one example of case study for safety related. See, nowadays, no, the shop floors are becoming more complicated, and it's all becoming quite huge. So there are human movements. There are also vehicles that are moving. Sometimes, see, like we are having a kind of opportunity for accidents on the road. There is a possibility of such kind of accidents that can happen in the within the industry also in the workplace when vehicles and human beings are moving, there could be a possibility of collision that can happen. There are blind spots when you go through the alley, huge factories, you can see that many walkways will be there. So there will be a kind of 90-degree turn where you will not be able to visualize. You can probably keep some mirrors and other things, but there is always a possibility of you skipping them, no seeing them, and there is a possibility of no hitting the humans. So the interaction between the vehicles and personnel or vehicles to vehicle transportation in industrial gangways poses a risk of accidents. That's what we are talking about. And this potential occurrence chance of accident is high. Severity is also high, which can even become fatal. And inadequate detection control to eliminate the potential accident. So, as I said, no, deploying kind of lens mirrors, bigger ones, and still there is a possibility if you are not seeing it properly, there is a possibility of vehicle to vehicle collision or man to vehicle collision. How these kind of situations are handled in industry, you can see here. When there is a human and vehicle interaction that's going to happen, the blind spot hazard is coming into picture. So you should you can deploy opportunities like there could be some kind of both audio as well as some visual thing that can come, which can alert quickly. So first it has to be draw some attention of the human beings, whether it is walking or driving the vehicle. You can see no the man vehicle collision point in the first picture, how it can happen. And if they can be before they approach the corner, if they can be alerted with some signals like the second one, what you see sign projectors, no stop projection, that will a light no that will come on the shop floor in a big way, as well as some kind of noise also will come, like no, please stop, there is a vehicle on the way, something like that, no, it can come as audio so that people can see it. This is what is shown in the third picture also. Alert system, indicator with a buzzer. There could be a siren also. So always it's good to have both visual as well as audio visual, because as human beings there is a huge subject called the kinesthetics. We human beings are not same. Some people are more prone to text matter. Some people are more visual people. Some people are more audio people. They can hear think whatever they can hear, they can memorize. Even in the education system, it is saying that no, some people, some children know they are more prone to have good memory when they are hearing things rather than reading things. So when you are using them in a proper way, both audio and video or visual, this can give the best effort. So safety systems detects like man and vehicle, stop sign signal projector for floor display that can happen. This system detect possibly the collision, gives alert light with a buzzer. That's what you are seeing in the third picture. So just to know, I'm going to show. It's a very simple picture. It's a before you put the alert system, how it is. You are going now, move towards a walkway, right? Imagine that you are a vehicle or human being, no, moving this walkway, and suddenly there is a vehicle, no, that is coming from other way. There is a possibility of you getting into an accident. That's what is happening before deploying this kind of system. Okay. Now the same thing, if you are going to adapt a kind of human machine interface, you see here. So I hope you have noticed when the vehicle is coming, even before you see that stop visual no that is coming, as well as there is a alarm that is coming up, so that you stop and wait for the other vehicle to move first. Then you can make the movement. So there are some other videos which are being used to know. This is all just for you to know, understand how automation is being used. Have you noticed? This is not human. This is manless. So you can see that this complete thing now this is programmable, so that previously when you have to carry a lot of weight, no, either through humans have to carry or vehicles have to carry. Now all this can be kind of uh, guided automatically. That's the way it is. So it's very interesting that, as I said, wherever repetitive jobs as well as uh, where a weight, for example, in this case, you can see that these tires are very special, so they are of huge weight. If they have to be carried, no, it has to be carried by a vehicle only, not human beings, not possible. But if they have to go from one place to another place in a repetitive nature, then it is possible for us to deploy this kind of vehicles which are programmed, and it can go without human intervention. Only for programming, no interventions is required. So this case conclusion, you can see here uh, how the transport system is taken care through this kind of HMIs. There are van system, no V2 vehicle to network, and then vehicle to vehicle V2V, then roadside units are available, and vehicle to pedestrian V2P. So all these things are being sensed. So AI based vision system can enhance industrial safety as well as even road safety by detecting and preventing collisions between vehicles and humans in real time. So it ensures AI. The difference between automation and AI is AI also can go, all possible options can be or simultaneously explode, and best of the option on a real time can be picked up, and it can be used. It ensures efficient operation by automatically alerting and intervening when potential hazards are detected. So I hope you found this case studies useful. Again, let me repeat: the subject what we are talking today is not a rocket science. This has come into existence, and it is on a kind of, if not, I will not be able to say that it has gone to a matured state, because with the advent of AI, uh, still there is a huge scope that is available for automation. But however, definitely for safety and uh, repetitive nature of the jobs, no HMIs have completely gone to the kind of mature stage. Um, so, what are the future works that are available in this space? Let us see. uh, Innovation in industry 4.0 has really created, you can see the brain computer interface, gesture recognitions are possible, haptics, I was talking about the haptics, no, with the movement of it's almost like virtual reality. When we see virtual reality, you feel like that you are on a kind of the games, you feel that you are driving the car, and a similar kind of thing you can do in industrial operations also. Assembly, without the machine before you, it is possible for you to visualize the machine on the all assembly operations, and you'll be able to execute. That's what is called haptics. And virtual humans who can address your problems. And role of AI in tutoring systems is great, and enabling seamless synergy between human creativity and machine efficiency to drive innovation, productivity, and decision making across industries. AI supports human at work. These are all what you are seeing here, and AI assists seniors at home with smart devices for daily care. All these things are happening. Even if you see during the COVID time, you know that many countries have um, restricted human movements outside. And I was told that during that time, Singapore, for example, if you are not able to really avoid traveling, and you are going for a meeting, and you are staying in hotel, you are not actually allowed to to go outside the room unless otherwise it's necessary. So actually robots were put into place which came to your no rooms, knock the door and give you the newspaper, or whatever you ordered as food, no, everything came. So definitely, I would say that COVID period has given a huge change in terms of deploying this kind of no automation into real life. So this plays a very vital role in ensuring ethical oversight, emotional intelligence, adaptability, and fostering trust in human care. I think all these things you might be knowing, but still I am reiterating improved efficiency. Machines perform repetitive and complex tasks faster and more accurately, saving time, right? So, um, and personalized experiences, AI driven system adapt to know individual uh, preferences. For example, smart devices and wearables, reduced human effort, automates no tedious tasks, and allowing humans to focus on very creative and high value activities only. And real time assistance is possible. Devices like smartwatches, assistants provide instant support for health and communication or tasks. Dependence on technology over limitations. No, whenever we say that any system you bring, there are pros and cons, and what are the limitations? That's what described here. Over reliance can reduce critical thinking and problems, and that's happening now. Today, I think at least in our generation, we were able to remember the phone numbers. Today, no more so. People don't even remember phone number because we are all having them. If you really misplace your smartphone, I think you feel miserable. No, immediately you feel that you are cut off. You are not able to do that. Similarly, calculators, with the advent of calculators, those days, no, we were not allowed to use even calculators in our college time when we did our engineering. Uh, but what happened is, with all kinds of this system comes slowly the human critical thinking also now getting into a problem. Learning curve. Advanced devices and systems may require time and effort to adapt. There is a kind of psyche, no, like fear culture that can come into picture during the learning devices. Anything that comes new, you would have seen elders still no, not preferring go to ATMs. Then they worry that they can really get these stolen off in the ATM kind of thing with the machines. No, people fear for this kind of unknown, it's called the unknown fear, right? That comes into any technology. Privacy concerns. I think I may not talk about this. No, cyber activities you would have seen. Collaborative systems collect and store large amount of user data, leading to security risk. This can happen. No, today your phone number is available to many people whom you don't know due to various systems. It could be your banking system where you are given. The data are being sold, and people can have access to your number, and they can bother you for many things. Cost barriers. Advanced technologies may not be affordable for everyone, so definitely there will be a cost barrier. Uh, and compatibility issues. Not all devices integrate seamlessly, creating frustration for user. I think any new technology comes, people have the problem. Even we have the problem with the remote. When we are operating the system, sometimes. I think this is a kind of a short presentation now. What I have from my side. I'll be happy to have any questions. It's a kind of very simple subject. My intention was not to really get into the technology part, but more on application part, so that now we can understand what is a human machine interface and how it is being deployed into industries, especially. Thank you.
Thank you.
Can I stop? Can I stop sharing so that we can see your faces?
Yes, yes. Thank you, sir. Thank you for informative presentation. Any questions from audience?
I'm happy to see good number of people have attending this program.
Yes, sir. First questions? Any questions from participants?
I'm seeing some smileys and some comments.
That's a nice presentation, sir. Oh, unmute பண்ணுங்க.
Okay, people are muted. Okay.
Yeah. Hello, participant.
Hello, sir. Good evening, sir. This is Venkatesan.
Yeah, English, please.
Sir, how cohorts and tandem drift, one of the recent, sir, tandem drift,
Mhm.
used in automobiles.
See, I have frankly no idea specifically about that.
Okay.
Uh, Bharanidharan, are you there? You have
Yes.
any kind of response for this?
Sir, could you please again repeat your question, sir?
So tandem drift that is used in that will be used in automobile like race vehicles.
Okay,
Sorry.
let
How
me see
that-
what is standard, then I will be able to tell you.
Sure.
Yeah.
And cobot and those things means both are like more similar or it will be mostly different.
No, I think they are different. I'm already seeing that in a tandem drift. It's a
Okay, sir.
competition where two drivers skid and weave their cars in tandem through a course while trying to stay close together without touching.
Yes,
But
yes.
basically, if you ask me whether it is coming under human-machine interface, yes. Unless otherwise there is a interaction, it's a more of no machine-to-machine interface. That's the way I'll put it.
Machine to machine, most probably. Yeah.
Machine-to-machine interface. So with a very large system now, we can use a lot of jargons are available today. That's the reason I did not understand because I'm not into this race and other thing. But
Okay.
The majority of the things, no, it's all coming under the so-called cyber physical systems. So cyber physical systems, as I said, no, just I'm going back to the basics. Cyber physical systems has kind of three ingredients you would have seen, right? Number one, you are collecting the data through sensors or whatnot, right? Whether you are measuring a temperature or speed or direction, whatever it is that you are taking. The second one is it is being synthesized with kind of analytics and other things. That's the second phase that's happening. The third phase is actuation. So you are trying to adjust your reaction to the particular situation, right? Through the best possible option. The biggest difference between, for simplicity's sake, now let me make this example. The biggest difference, there were times where only human beings were doing everything, right? There are times now where human beings and machines are existing together. Okay, this is what we are calling it as human-machine interface. And there are going to be times where only machine-to-machine interaction can happen. So they will be able to adjust. For a very simple example, you remember cars when they are being manufactured. There is I don't know the numbers. It could be something like 300 or 400 welding that can happen on the whole frame. No, that was happening. Humanly, it is a very kind of very difficult task. No, really to do consistently in the same way with the accuracy, right? This is getting replaced completely by robots now, welding robots now, which are million times they can do the same thing with the same kind of accuracy and consistency level. That is the biggest advantage. So all these things are coming under cyber physical system. The only thing is whether it is if it is going to be for enabling the humans to do, then we call it as HMI. But if it is going to be machine-to-machine interaction, then it becomes more of I would say IoT or it's all Internet of Things.
Okay. Thank you, sir.
Welcome.
Any other questions from participants?
Silence. Okay.
There is one question.
Sir, in chat box, some questions there. What is the basic difference between machine learning and HMI?
Okay, HMI, the machine learning okay, let me put it, I was talking about the repetitive nature, right? Whenever repetitive nature is happening, the machines can learn on, it's like a spiral. You imagine this way, no? Let me answer you in a different way. The difference between intelligence and artificial intelligence, you see that, no, both are different. Human intelligence and artificial intelligence, they are different. Similarly, what happens is in machine, when artificial intelligence is happening, the more data, it is becoming more accurate. That's what is happening. Any artificial data today, you are all having smartphones, right? If you go inside and see, you would have seen Meta AI, right? You'll be able to ask questions and it will give the answers. But many of time you will see that the answers which are coming out will not be so accurate. They'll be in very generic in nature. How so? Machines are also learning. When they learn, the number of points or number of data points what they are getting, depending on their accuracy levels is getting and better. This is called something called spiral. See, the more data points are available, they will be able to adjust and come to the exact answers at some point of time. It's something like having millions of options and trying to take the best one out of that. So machine learning is a process by which this artificial intelligence is becoming predictive in nature, whereas human machine interface is, I would say, it is a engagement between the humans. As I said, no, if a robot is put uh, to enable a human either to conduct an industrial activity or a surgery, those kind of things are considered as HMI. While machine learning is the process by which the intelligence is becoming more and more better over a period of time when the data points are getting better and better. I don't know whether I've answered you sufficiently. This is a kind of basic difference.
How to control driverless vehicle for AI?
For
AI, artificial intelligence.
driverless vehicle, for, see, technically I will not be able to answer. I'm not from that field. What will happen is, on a perceived way, just to let me know how AI can be adapted in manless driving. That's what you are asking. Have I understood your question correctly? How AI can be adapted in manless vehicles? Am I right? Yeah. So this is something like that. So let us say that again, if you are just a human driving, the decisions what you make is by your visual systems, right? By seeing, by hearing, right? All those things only you are taking a decision. That's what is happening. So in manless vehicles, again, the data points have to be enlarged. Once you enlarge that, these data points also will create a kind of intelligence to find out what are the possibilities that happens. So one thing, the difference between a human brain works in a different way. The machine intelligence, whatever we call it as artificial intelligence, it works in a different way. So this, the real time when you are collecting the data, the depending on the speed of the collection of data, you can, for example, through sensors, you can decide to take even every millisecond on data, or every minute on data, or every 1 hour you data. All it's all depending on what you want. Okay, but data by for the sake of data, you cannot take too much of data. It becomes a big data. Then you need to have a storage also, right? It's huge. The cost of storage of data is going to be tremendous. Nowadays, it's all in cloud, and clouds are costing hefty for industries really to have that. Coming to AI portion, these machines which are moving, manless, when they are having, it's all intelligence. They are, by technology, using advent of technology, they are going in a kind of structured path. By AI, what is happening is this can become more predictive. they will also know with the signals, whatever data they are collecting through various sensory systems, they can get many options on a real-time basis, based on which they also will start thinking on its own and take the right decision and go. So usually any automation start with more human intervention and less automation. Slowly, as they become self-sustainable automation systems with the data points, whatever they are having, then this AI can help them to work on their own way. Let me give another example which you can understand more better. Let us say that you want to create a security system, intrusion detection system. There is a house, or let us take a country, India. We have Bangladesh border, we have Pakistan border, those kind of things happening. So in that, it is possible for you to make a physical fence, right, for disallowing people to go from one country to another country, right? Illegal way. That's a way. What's happening now is there are systems which are available, technologies available to alert with vibration sensing and with the cameras, intelligent cameras, to detect if this kind of intrusions are happening. There, how AI is being used is these instruments, when once the vibration is coming, there is a machine learning part which is getting into that, which makes it more intelligent to say that whether the crossing is by animal, or is it by a vehicle, or any kind of digging is happening around that fencing, right? So with this, you are able to classify the data. The machine learning makes it more knowledgeable, and it classifies the data and says that there is a serious intrusion activity that is happening in the border. The same way, if you are taking a manless vehicle, when you are employing a manless vehicle, it will actually, one of the slides I was showing that vehicle to human, vehicle to vehicle, like that, there are kind of different kind of connections, they are all seen simultaneously, collect the data, and what is the best option available for really managing such kind of situation, the decision is being made. Slowly, at some point of time, it is expected that they will be able to think, if not as human, almost like human, these machines can think. So AI is frankly making the machines almost like human. That's what is happening. We are going towards that. So slowly from, I would say, reactive, now it's becoming more predictive, and it also will become prescriptive, which means it will say long before the action happens, this can happen. For example, even there are the machines, the tools, for example, the tool, if you are doing a molding process, you can, today systems are available to say that probably 15 days from now, or after 15,000 operations, this tool can become out of action. So once this kind of prescriptive thing comes, it is possible for you, without doing any damage, you'll be able to act on that. For example, you can have a replacement so immediately, so that production is not getting stopped, or the machine is not getting damaged. So anything, whether it is a manless vehicle or industry or intrusion system, anywhere, all this artificial intelligence is going to help them to make it more predictive and prescriptive. Probably that is the best answer I can give.
Thank you. Thank you for a nice presentation, sir.
Hello, sir.
Yes, sir.
Myself, Dr. Manish.
Yes, Dr. Manish.
Sir, I want to know, there is a lot of autonomous vehicles coming, but there is certain collision problem. Like we are if having a car in a hilly area, then it will be major problem for sudden colliding. So, is there any standard for testing? What will the response time for the autonomous vehicle to respond that sudden collision, get obstructed from sudden collision?
See, this is a very evolving area. I will not be able to answer you straight away without knowing the case. I am not an expert. Let me tell you, I am not an expert to tell that. This autonomous vehicle itself is a very evolving area. We have not really. It is not in a mature state. If it is in a mature state, already it will be in the streets, right? So it is not happening. They are all being used in a very calibrated way. The kind of slides what I have shown you, for example, where for industrial purpose and what we call this automated guided vehicles, no, where instead of human beings transporting material from one place to another place, we are doing it. Autonomous vehicles, when they are coming into, your question is, what is the kind of response time before the accident happens? That's what you said. There, as I said, that there are going to be millions and millions of data that is collected by this vehicle. Somebody has to mute, I think. There is a disturbance in the audio system. Is it Mr. Yogesh Patil? I'm seeing. There's a kind of background noise. Yeah, sorry. Thanks. So, autonomous vehicle definitely will have this kind of challenges initially. Because the response times have to be adjusted, between the sensing and action. There is a kind of lag that is happening. So the capability of the speed of the sensing and the speed of analytics and speed of reaction, that matters. So if you ask me very accurately what is going to be the time and what is going to today, I don't think unless otherwise we have a kind of real case before us, will not be able to answer. But one answer I can give you: is it possible to avoid such kind of collision? Yes, it is possible. Okay, it is a matter of adjustment between the sensing time to reaction time. So if you ask me for as a technology, if you see that it is always possible to adjust the speed, but over a period, there are a lot of failure modes that has to be seen over a period. It happens with the human beings, whether accidents are happening or not happening, right? So you cannot say that with machines. This thing, something can go wrong also sometimes, right? So technologies are coming. Say, for example, we are using today cameras. More cameras are deployed for sensing in automobiles. But in a fog, a country like let it be Germany or US, in a cold time, cameras also can have fog so that your sensing can go wrong. So now there are technologies that are coming like wave radars. Those kind of things are being deployed for very accurate measurement rather than going by cameras. So every technology challenge has also a technology solution. So there will be something which will be invented for tackling such kind of problems. Hope this answers your you, Dr. Manish.
Yes, sir. Sir, I request also please share the slides. It is very informative. It will be helpful to all of our participants.
Anything else?
No, sir. Thank you, sir. Just I request to please share the slide with us, sir.
Okay. Thank you.
Let me invite Dr. D. Sivaraj, Associate Professor, Department of Surgery, to conclude the session.
Thank you, Vale, sir. It is a great honor to deliver the vote of thanks for this session. On behalf of the management and Department of Electrical and Electronics Engineering, I would like to extend our sincere gratitude to Dr. Balaji Venkataraman, sir, for sharing his valuable insight on collaboration of human-machine interaction in real world with case studies and real-time videos. Finally, a big thank you to our audience for your active participation and enthusiastic questions. Even more meaningful. Thank you all once again. Thank you, sir.
Thank you, sir.
It's my pleasure. Thank you, one and all. I'm happy that so many people stayed in the evening time to hear. As I said, it's not a rocket science, so I hope these examples, what I have given you, help you to understand as an awareness session. Definitely, it's not a technology session where we are going to talk or we have spoken about the technology behind such kind of HMI. It's more on the application side that I have dealt today because this time period allows only that much, right?
Thank you, sir.
Thank you, one and all.
Dan, sir?
Can you unmute? Are you able to hear me, sir? Hello?
Good evening, sir.
Hello? Good evening, sir. Yeah. Hope you could able to hear me, right?
Yes, sir.
Yeah. Okay, sir. Yeah.
Dear participants, and we are entering into the session 4, Advanced Manufacturing Technologies, that is 3D printing, CNC machine and robotics by Dr. Dan Satyaraj sir, Associate Professor, Indian Institute of Technology, Indore. In this August occasion, I invite Mr. Nanavil sir to introduce our speaker to the participants.
Good evening to all. Good evening to all. I am Jonavin, working as an assistant professor in the Department of Electrical and Electronics Engineering at Sri Manapulavan Engineering College. It is my privilege to introduce our speaker, Dr. Dan Satyaraj sir, for today's session. Dr. Dan Satyaraj sir is working as an assistant professor in the Department of Mechanical Engineering at IIT Indore. He completed his PhD in the year of 2016 from IIT Hyderabad in the area of thermomechanical processing of high entropy alloys. So before joining IIT Indore, he was working as a postdoctoral researcher at TU Dresden, Germany from May 2017 to November 2019. His postdoctoral research was funded by the prestigious Alexander von Humboldt Foundation. His research area of interest: advanced manufacturing, micro nano machining of high entropy alloys and additive manufacturing of these advanced high entropy alloys. He has published more than 30 papers in international journals. So we are honored to have Dr. Dan Satyaraj sir with us today to share valuable insights and expertise that will enhance our knowledge and skills. Sir going to give fourth session today with the topic of advanced manufacturing technologies, 3D printing, CNC machining and robotics.
Okay, sir. Thank you very much for introduction, sir. Hope my voice is clear, right? Because someone is putting in the comments the voice is not clear. I don't know.
It's clear. Now it's clear.
Now it's clear, sir.
Okay, fine. Then I can start my session. So already I told today I mostly talk about my research related talk, mostly what we are working in the additive manufacturing. So basically the talk will be like the additive manufacturing for advanced materials. Maybe you can take it like this. I hope yesterday a little bit we covered this robotics. I told about the introduction about robotics, how we can automate we can do that. So mostly I told about it. So today mostly I will talk about in the research point of view in the additive manufacturing. Okay, so I will start with the introduction to additive manufacturing. Then I will just go ahead with the what kind of work we are doing and what kind of research we are doing. I'm going to present our results. Okay. Hope this is the outline of the talk today. Like I will start with the introduction to additive manufacturing. What is powder-based additive manufacturing? What is wire-based additive manufacturing? I will just briefly I will talk about the basics. Then I will go on to the what are all the materials in the forthcoming era? What are all the materials for the additive manufacturing? Mostly I will talk about these multi-component alloys, and then I will just present what are all the work we are doing in the IIT Indore. Okay. So I hope we had to go for advanced manufacturing. We may know that like mostly like we are having this limitation in the conventional methods we need a very high tolerance and product requirement. Also, we need a high production with low cost, so that's why people wants to go for advanced manufacturing. So this is one of the additive manufacturing is the one of the advanced manufacturing process to fabricate the complex shape. So hope all of you know about that how they will make the additive manufacturing. So it is called it like layer by layer deposition. So usually we will deposit the material by layer. Then we can make a any kind of complex shape. Okay. So for that, first we need to start with the design, and then idea. Like you may design the component by the idea of the CAD software. So nowadays many CAD softwares are available in order to draw this. So whatever the model, then from this CAD model, the software itself it will convert to the machine language. Then it will given to the 3D printer. So directly it will print the whatever component we want. Okay, like we have the here we have the kind of the design freedom, and whatever the complex shape we can easily make it by layer. So okay, so nowadays almost any material can be processed by the 3D printing. This is the broad classification of the additive manufacturing technology. If you see, based on the raw material, we can make it to three different groups. One is liquid based, and solid based, and powder based. If you take liquid based, mostly like kind of all these polymers, plastics will come under this. Like kind of again in liquid based, there are two types are there: melting and polymerization. Based on polymerization, there is technology, stereolithography, polyjet. These are all certain 3D printing technology. If you come to the solid base, then LOM is there. Or if you come to the powder based, in case of belting, there are different techniques are there. Like all are related to laser, like selective laser sintering, belting, direct laser metal sintering, and electron beam melting. These are all the coming under the powder based processes, and binding also we can do that. Okay, like so these are all certain classifications. So because why we have to go for additive manufacturing is it is one of the very key component or one of the pillar for the industry 4.0, because it is also coming under this 4.0, where it is the role you can see in this particular diagram, because it produces the very less weight. The wastage of this material is very less in case of additive manufacturing, and also we can decrease the prototyping time and cost. Also, it may promotes the business digitalization. We can synthesize the assembly. No need of assembly process. We can make it like a single part out of it. So these are all certain advantage. These are all the broad classification of this additive manufacturing. We have these 7 technologies, like 7 groups. So if you take first 4, mostly these polymers are used, like binded jetting, material jetting. These are all polymers. People may use it. In case of direct energy deposition, people may use powder based or wire based. Both kind of raw material we can use in the direct energy deposition. So I'm going to briefly, I'm going to tell you what is the meaning of this, where we will use this kind of additive manufacturing technologies. Then I will go ahead with the some of the how it will look like. I will show the process. Okay, so these are all certain technologies like powder bed fusion, sheet lamination, wet polymerization. Okay, so already I told the stereolithography is mainly it is coming under the liquid classification. Mainly here we will use the photopolymer resins. Okay, in case of photopolymer resin, directly the laser will fall on the resin. It will cure the particular resin material. Then it will become a solid. So in that way, layer by layer, you can cure the material and you can make any component out of it. Okay. So in case of powder-based system, there are so many techniques. Is there one of the most popular is the laser sintering method. Okay. In case of laser sintering, you can use the any kind of powder here. Okay. So if you go for laser sintering again, the size of the powder should be it should be in the nanometers. Like also it should be in a globular shape. Then only you can make it can flow through the nozzle, or it can like layer by layer you can deposit it the bed. Okay. So you can use a variety of material in case of laser sintering. titanium or polyamide or any kind of suppose if you have the raw material in the loose powder, then you can use this material as powder based fusion or sintering. You can use it. Okay, in case of material jetting, it's look like a printing machine, like kind of inkjet printing machine. It will distribute the like whatever this melted droplet of this material. So photosensitive material it will deposit, then it will solidify it based on the ultrasonic light. So basically this thermoset photopolymers, this and all they will use it in the material jetting. Binder jetting also similar to that kind of. So you can use the in case of binder jetting, you can use any kind of ceramics or metal also can be used as a raw material. Okay. So in case of direct energy deposition, already I told there are so much of classification is there, like all powder based process and in case of wire arc additive manufacturing also will come under the direct energy deposition. Okay. So in this case, so basically you may use a powder or wire as a raw material. Here the source will be like you have to melt the powder or wire, right, in order to deposit the particular raw material. So for that you can use the laser as direct source or electron beam also you can select it. So that will basically it will melt it and then it will cinder the layer on a substrate. Okay, that is the basic thing. So here the powder deposition is basically it is synchronized with the what is the available heat source. Like here the laser or electron beam will be act as a heat source here. Okay, so here basically we don't need a kind of powder bed fusion. So in this case it can pass through the nozzle, then it can completely melt. It will deposit over the any kind of substrate. Okay. Uh, but if you go for fusion and all, maybe I can show with the example like fusion based technique, powder bed fusion and all. If you take there, you have to take a powder in a bed. So in that case, you need a lot of powder is needed for the in case of powder bed fusion and all. We need a lot of powders are needed for deposition. Okay, so that is the advantage here. Like in case of this direct energy deposition. Okay, so 3D printing again. Already I told about how we can do it. Like first you have to make a CAD model out of it. Then we have to slice the object. Then we have to create a kind of it should we have to convert into STL format. Then you can convert into the any kind of machine language like G code, M code. Then directly it will given to the 3D printing technology. Okay, in order to print the sample. So in case of sintering, already I told like here people won't melt the sample. In case of selective laser melting, they will melt it. Then basically they will deposit. That is a main difference. Okay. In case of fused deposition, again here also people won't completely melt the sample. Basically here also the sintering process will happen. In direct metal deposition, again you can take it in a powder form, then you can pass it through the nozzle, you can deposit. Okay, so these are all the different types of additive manufacturing technologies you can see here. Uh, Also wire arc also one of the example for the DED already I told. So in this case, instead of powder, we will send the wire as a particular feeder. Okay, like here you can choose the any kind of diameter of the wire. Like the diameter of the wire can vary between 1 to 3 mm. So based on that, your bead size will differ. Like maybe I will show it in the next slides. So here the advantage of this RAM is basically you can the deposition rate is very high in this RAM, and also you can use any kind of robotic arm or machine based tool you can use it. So in that sense, the bed will be very large. So you can do a like very high component. You can Like what I try to say is like very large diameter or large sized components can be easily printed in the RAM. So also the lead time also like you can reduce it, and material efficiency also good. Also the porosity also like you will get it in a very less as compared to the powder based process. That is the advantage of the VAM. Again, VAM here, what kind of technology they will use, it means like I hope you may know about this basics of the welding. They will use this concept of the heat source will be the welding source here, like kind of they will generate the arc by using the electric current, or you can use some kind of like TIG based system or MIG based system. So those kind of things you can use it as a source, and so you can melt the particular wire and then you can deposit over the any kind of substrate. Okay, there are different kind of VAM based techniques are there. So here gas metal arc welding is one of the type, and cold metal transfer is the one of the short circuiting method. So like this, there are different kind of welding type is there. So based on that, you can do a additive. Okay. So this is the thing. So this is a little bit about the short introduction about the VAM. So here you can see the, so what is this? What is the laser powder fusion or selective laser melting? So here you see the powder is kept in the bed. Okay, like all this, all are same process. Suppose here they are manufacturing the gear. So you see here the all the raw material are powder. Here they kept it in the bed. So over it, the sintering process is happening layer by layer. After each layer deposition, the bed is going down. Keep on like basically it is something like a piston cylinder assembly. The piston is going down and then keep on the layer is adding in the particular each layer. Then finally we could able to make a gear out of it. So for that we need a large amount of powder in this particular bed. At least we need a 2 kg or 3 kg of powders. We have to fill it in the particular bed. Okay, in case of fusion or selective laser melting process. Okay, but in case of direct energy deposition, so in this case you see the diagram here. Basically here the powders are passing through the nozzle. Okay, so because of that all the powders will melt in the nozzle itself. Then finally it will come out in the melted stage. Okay, so then you can easily deposit. So basically we will use two types of a process like TIG based or MIG based. So in it is nothing but TIG based means is a tungsten inert gas welding. So tungsten case means the tungsten will be act as a electrode. Then so basically so the raw material will be flow from the outside. Okay, so in case of if you take gas metal arc welding or metal inert gas additive manufacturing, so in that case the source will be your electrode will be act as a consumable. So directly it will get melt and it will deposit in the substrate. Okay, in this case tungsten TIG case the electrode will be separate and you have to feed the wire separately. Okay, so here in metal wire arc or in case of MIG process, directly the wire will be used as a electrode and substrate both same. Okay, so here basically they are using the laser for the melting the powder. Directly they are melting and depositing in the circular component. You can see that how they are making the circular component. So this is the thing basically I'm discussing. Okay, like you can use any kind of like a different technique, TIG based or gas metal arc welding based additive manufacturing. Okay, so the typical setup will be like this. So usually you have this electrode and you have to pass the argon gas for the shielding of the your sample. So over the substrate, usually layer by layer, you will deposit your sample. Okay, also you can use a plasma arc also you can use it. That is called it like plasma arc additive manufacturing. That is also like work like TIG based process only. Okay, So these are all certain wire-based additive manufacturing process. Okay. Now I'm just coming to this difference between these both method. So if you take each method has certain advantages and disadvantages. Suppose if you take powder-based process, so you can do a variety of metallic materials you can deposit, or different kind of materials you can deposit, ceramics, glass, plastics, you can do it uh, if it is in the powder form. But in case of wire form, the advantage is like it has very good high deposition rate, and there is no dimension limit. Already I told we can do a very large size component, you can easily make it economically. The costly material, for costly material also it's economic process, very less health hazardous, because we are just melting the wire here. So limitation if you take, so in case of powder base, it has very the printing time is very high, means very slow process. The porosity level is might be much higher as compared to the VAM. Uh, so also the smaller lower powder utilization you have to do, that is very limited. But if you come to the wire base, the limitation here is mainly the process parameters. The process parameters are very highly sensitive, and the position of the wire is particular to size and shape. So that can be sometimes it's very difficult. Also, we cannot get all these samples in a wire form. So basically, in order to produce this method, we need to take a raw material in a wire form, but we won't get it at like sometimes ceramics we won't get it in a wire form, or some of these brittle material we cannot get it in the wire form. So in that case we cannot do the wire based technique. Okay. So nowadays a lot of materials are available for this additive manufacturing. So nowadays people are focusing on many different alloys. For example, still people are looking for this nickel super alloys. It is mainly used for high temperature application. And if you go for automobile or aerospace application, still the aluminum alloys, titanium alloys, or stainless steel are very steel alloys are really popular, and people are still working on this in the particular additive manufacturing. And also people are working in this high entropy alloys also, or multi-component. It's called it like multi-component alloy. So in case of metal and alloys, it is people are really focusing. In case of smart material, mostly the people are focusing on piezoelectric material or sim memory alloys, or some kind of civil structures also. Like people are, I hope you may hear about this. People are making the 3D printing of home. You can nowadays we can create our all this concrete and everything. We can just print it by 3D printing directly. You can make a house out of it. Hope I think the IIT Madras they made one of the office room by 3D printing of this concrete. They made it one of the building. Okay, so also it is very popular in the hydraulics and electronics also. People are trying to make this multi-material printing connectivities. So that's all they are trying it in the additive manufacturing. So now I'm coming to the so why we go for advanced material for the this additive manufacturing. Okay, so like what is the use of this multi-component alloy? I just like to present, because mostly I'm going to talk about this multi-component alloy. Okay, so basically if you take any conventional alloy, mainly it is based on the one dominant element. Okay, like for example, if you take steel, the iron will be a major proportion, and it may have other alloys like other component like magnesium, manganese, or carbon, or some other elements will be in a minor proportion. Okay, so mostly if you take conventional alloy, one or two materials will act as a principal or a dominant element. Remaining other elements will be added to enhance the particular properties. Okay, but in case of this particular multi-component alloy, all the elements are acting as a principal element. Like for example, what I'm trying to say is like suppose if you're taking a four component or five component alloy, for example, cobalt, chromium, iron, manganese, nickel. This is the five component I'm taking. Suppose if it is near to the all are 20 percentage means that is called it like a high entropy alloy. Okay. Uh, so so usually these alloys have five or more principal elements. This atomic percentage you can vary between 5 to 35%, because initially people told that it should be near ecoatomic, means suppose if you're taking five component means you have to take 20%, but in order to enhance this design flexibility, then after that people try to make it like if it is between 5 to 35%, then it is called it like a, they call it like a high entropy, right? Because the name basically it's come from the configurational entropy of the system. Okay, so basically if you mix the multiple elements, the configuration entropy of this particular system will go up. That will reduce the Gibbs-Finney energy. Okay, so because of that, like you can maybe I can show this formula. Yeah, this is that for Boltzmann hypothesis on the relation between entropy and the complexion of the system. So here basically n is the number of elements and r is the universal gas constant, and del s is the configuration entropy. So it is directly proportional to the number of way of mixing or number of components or elements. Suppose if you are adding more elements, that will increase your configuration entropy, which in turn that will, so you can see that like when you are increasing this configurational entropy, how this configurational values are increasing here, you can understand here. Suppose if it is crashing 5 elements, then the value is crashing like 1.5 r, okay, 1.61 r here. So that's why it is called it like a high entropy alloy. Okay, so this is the basic guideline. So also maybe I can show you about uh, sorry. Um, so already I told like suppose if you go for, if you increase this configuration entropy, that will decrease this Gibbs free energy. Because of that, basically it is forming a very simple structures. Like you may expect like kind of multiple crystal structure in that particular component, but usually this multi components are giving a very simple structures like BCC or FCC or different kind of FCC or B2 phase, like this very stable structure it is forming. So because of this stable structure, so we are getting like kind of very different properties out of it from this particular alloy. So why? Because means it has this particular core effects as compared to the other conventional alloys. So already I told about this configurational entropy effect. Also, second one is the way it will stabilize. For that, already I told about this configurational entropy. So next is like, so when you are mixing the many elements, they try to see the atomic size is different, right? Like when you're taking the different elements, the atomic size of this each alloy is different. Then usually this will give a very distorted or strain lattice in the system. Because of this strain, particularly this will increase the strength of the particular system. Strength or hardness may go up, and also so when it is many elements are together, that will make a very sluggish diffusion. Means very slow diffusion will happen. In that sense, you can control the microstructure. Okay, like very slow grain growth means the microstructure growth will be very slow here. So because of that, so basically this alloys will work out in the very high temperature application. Okay, suppose if you go for very high temperature, the grain growth will be very limited. Because of that, you can use it for high temperature application. Then the fourth core effect is the cocktail effect. Basically, this term was proposed by our Indian scientist, our IAC professor Ranganathan. So when you are mixing multiple elements, that might be produced like a cocktail effect. It may give a different property than conventional, like what is the base material. Okay, like it might be a microstructure or it might be a material combustion, electronic structure. So it can, it vary that. Okay, so now you may ask like if I mix these 5 elements, maybe whether I may get this hydropy or not. So most of the systems are giving a very stable crystal structure, but some of the systems are forming a very complex system that we cannot study. So these are all based on the crystal structure. People are nowadays they are trying to classify this particular multi-component alloy or high entropy alloy. Suppose if it is related to the 3D transition metal, this is called it like a FCC group. Okay, like for example, cobalt, chromium, iron, manganese, nickel based kind of elements will form a FCC based structure. Suppose with the 3D transition metal, suppose if you are mixing any kind of large atomic size elements, then it will form a multi component. Like it will form a FCC with some kind of B2 phase or BCC phase will form. And third group is the refractory metals, like all this caphanium, niobium, titanium, tantalum. All these refractory metals are basically it will form a PCC structure. Okay. So another group is palladium, cobalt, iron, nickel, palladium. Some of these alloys will form FCC. Some all these other alloys they kept it in the fourth classification. Okay. So like this way, people are nowadays they are trying to classify this particular alloy. Uh, so again, so if you see this, why I am presenting about this advanced material means, if you see the property, it has very good structural and functional properties. That's why nowadays people are much focused on this particular alloys. Suppose if you see the mechanical property here, the yield strength is much higher than the other conventional alloys like titanium or stainless steel. As compared to the other conventional alloys, some of the system is having much higher yield strength and good ductility. The fracture toughness is really high in this high end alloy, even as compared to the certain ceramics and alloys. The wear resistance also good. Already I told about this high temperature application because it has very sluggish diffusion. So because of that, the structural stability is much good. So it can retain this microstructural for very high temperature. Because of that, the strength will retain at very high temperature because of the resistance to the high temperature or annealing. Also, the high temperature wear resistance also good in this particular component because of this lattice distortion effect. Already I told. So not only bulk material, people are using it in this coating also, because suppose certain base metal you may need to use it. So for example, automobile or aerospace application, we need a light material. For example, aerospace, this titanium 6Al 4V and all used in the aerospace application, but at the same just for the weight reduction, just you can do a coating and then you can change the surface property in the surface level. Suppose if you want a very high hardness, then you can deposit this different type of HES, then you can enhance the surface properties. Like this you can work on this film, or nowadays this high entropy bulk metallic glass also very popular. Again I told about this refractory alloys. Refractory high entropy alloys are mainly used for high temperature application. Again, the refractories are usually have very high melting point. Because of this high melting point, you can use it for the very high temperature application. Okay, so also you can use this high entropy for the cutting material as a, because already I told some system is having a very high hardness. Because of that, you can use it like a, very cutter or tools. uh, so for that purpose you can use it, like instead of cobalt
Sir,
here. Yeah, please.
slide,
Hello, please.
slide, can you enlarge it, sir?
Slides are not able to see.
Yeah, sir.
Okay, so are you able to see now?
No, sir, I think
Are
it
you able to
is.
see now? Not able to see. Okay,
I think it is not easy, sir.
wait a minute. Now?
Yeah, now it's okay.
Okay, I don't know, so sorry. So hope you got some idea about what is high entropy, right? uh, I think up to this it is visible. I hope you got the idea about what is high entropy. So it is nothing but what I try to say is it is something like a multi-component alloy, so because why it is very popular nowadays means usually these alloys are forming a very stable structure, and uh, also it is forming a particular crystal system. So because of that you can easily you can improve the property of this particular alloy. Okay, so also I told about certain core effects. So it has as compared to the other conventional alloys, it has certain kind of inherent properties. So because of that, so you can get a very good structural and functional property out of it. That's what I try to say it. So now I'm just coming to the so what is like our little bit our whatever our work. So basically we are not working this 5 component system. Just we want to a little bit go down, and then we want to start with the medium entropy alloy. Medium entropy means basically here we have taken this 3 component like cobalt, chromium, nickel. Okay, this we have taken in a equiatomic proportion. Then we try to see this property, but this alloy is really popular because it is giving a better property than some of the 5 component alloy. That's what we try to manufacture this particular alloy in the through the additive manufacturing process. Okay, we tried in the both process, like in powder based additive manufacturing, and then by using the um, wire arc additive manufacturing. Okay, I will just show the what are all this LED process we did, like laser based direct energy deposition we did in this particular alloy. I would like to show that study. So why we started this alloy means when we are starting the work, mostly people studied this only 5 component alloy. Like people try to deposit through the additive manufacturing. They try to do this cobalt, chromium, iron, nickel, manganese based HEA, or other 4 component system people studied. They understood the certain mechanism. Okay, still large gap is there in that particular alloy. So they try to study the as deposited sample. They never did any kind of process parameter change, or they not studied mechanical property in depth. So in that point of view, we started this particular research. Okay, so basically they not changed any process parameter, and then they have not did any kind of modification in the particular alloy system. Like so, for example, you can vary this combustion by changing this atomic proportion. You can vary this combustion, but people are never studied, and also people never look into the post processing technique. Suppose if you are going with the additive manufacturing, usually you have to do some kind of post processing like heat treatment or surface modification technique. These are all the things we need to do, because usually the surface you won't get a smooth surface after additive manufacturing. You have to process it. So that also people never look into it, and also people never studied about corrosion property also in this corrosion fatigue. This property also never studied. So in that point of view, we started this work. Okay. Uh, for example, so this is the basically our research objective in this particular alloy. So we try to optimize the process parameter through the LED process. Basically, we have did the microstructural nano indentation study. Like for example, in the macro level, to understand, we did a microstructural study by SEM, TEM, EBST, some of the characterization technique. These are all, and also in order to understand the nano level, nano indentation study also we did. Also, we changed some process parameter like interlayer scan rotation. We try to change the scan rotation and try to see the how the mechanical properties are changing. And also we try to change the combustion also. Means we have taken cobalt rich and cobalt lean in this particular 3 component, and then we try to see the what are all these microstructure and structural property change. Also in final, we try to see the how this kind of laser shock spinning, like it is one of the surface modification technique, how the spinning is effect on the particular additive manufacture sample. Okay, also we did some post processing by cryogenic or heat treatment. Also we tried. Still, our students are working in this particular wear and corrosion study. Okay, I will try to show you three or four objective what we did, what result outcome we got it. Then I will just go ahead with the some of the high entropy results. Okay, uh, so this is the basic setup. What is laser DED setup? What is available in RR gate? So we are just collaborate with Professor Dr. CP Paul. So we with this collaboration we did this additive manufacturing of this particular alloy. So this is the system what is available there. So here basically we have this laser source. You can see a nozzle here. Okay, so basically here it is a system. Everything is covered in the leak proof chamber. Okay, with the glove box. Basically they will fill the any kind of environment or they will make a vacuum. Okay, they will create a vacuum inside the chamber. Okay, so now I'm coming to the how we did the deposition. Okay, so initially we have taken this we pre-mix this all this powder, like we have taken this cobalt, chromium and nickel, these three powder, and then you can see that it is in the spherical shape. We have taken in a near equatomic proportion, like all are 33 around in that proportion we have taken. All the you can see that all the powders are around 50 nanometer, like something like this. You can see that almost it is in between this 50 nanometer. These are all the parameters we used. There are different laser power we tried, and also we different scan speed also we tried in the DED system. Okay, like we try to vary between 700 to 900 volt, and then scan speed is we kept it in between 0.3 to 0.7. Remaining other parameters we kept it similar. Okay, powder feed rate, gas flow rate, stand-up distance, everything we kept it very similar. This is the first raw material we have taken as a powder. Then we deposited. So you can see that already I told we vary this laser power, right? We vary it between 700 to 1000 watt, and also the scan speed also we can vary this. This is basically over the substrate we have deposited this particular sample. Here you can see that bead of this particular deposited sample. You can see that. So based on that, based on the porosity and then this bead height aspect ratio, that is called like this. So based on that, we decided that this parameter is giving fourth parameter is giving a better bead height and width, and also the porosity levels are much lower in this particular condition. So in that particular laser power and scan speed we have taken, and then we use it for the particular deposition. Okay, like we deposited layer by layer. We could able to do at least 20 layers. We could able to deposit 20 to 30 layers. We could able to deposit, and also we have taken a sample in a different direction. Basically, we will call it like scanning direction and building direction. Along the building direction and the scanning direction, we have taken the sample and then we characterize the microstructure by EBST. Okay, when we are seeing the EBST, what we understood is like in the scanning direction, most of the cases the grains are little bit all the grains are elongated, very coarse structure. But in case of building direction, almost all the grains are in a gallumular, like kind of you can see that gallumular grains, like epitaxially it is grown, and also interestingly the texture is really very different. Okay, in the building direction the texture is almost you can see the same color, like same color means all the grains are oriented in a similar orientation. Okay, so this texture also will play a very important role in the your property, structural property or functional property. Hope you may study it. So this here the texture is really very same. So sometimes it is the we need a specific texture. Some cases, suppose for example, if you need a isotropic property, for example, all direction I need a very equal property means I need to create a sample such a way that random orientation. Okay, the random orientation samples are usually have a isotropic properties. I hope you may get this. What is the idea of isometric and anisotropic material? Isotropic means all the sides you will get a equal property. Basically, this kind of textured sample will give you anisotropic property. Means specific direction the strength might be good, and other direction the ductility might be very bad. So these are all certain disadvantage of this texture. Okay. Um, so that's what we get as deposited sample. The building direction is giving a kind of very coarse structure with epitaxial grain growth. So now we try to see the inside the grains. We try to see a nanonotation. Like we did a nanonotation and try to see the property hardness. So it is not much varying with respect to the different strain rate, or with respect to different direction also, like scanning direction or building direction. If you see, it is something like 280 and 290. It is not much difference. Almost similar kind of things we got it. Also, we try to do the strain rate difference also in the harness. So we are not seeing much difference. Okay, like almost we got a very strain rate sensitivity is much less, 0.04 or 0.03. This is very typical for the this multi-component alloy. So usually this multi-component alloy will form a very low strain rate sensitivity, and also the activation volume also will be very less. For example, if you take conventional alloys, this activation volume will be in the range of thousands B cube, but if you take high entropy alloy, this activation volume will be in the range of 100 or 100. That's what we observed in this particular medium entropy alloy also. Okay, so mainly these factors are contributing this. We determine from this outcome of strain rate sensitivity and activation volume. So it is basically the chemical short range ordering in this particular alloy is playing a very important role, and paralysis barrier, lattice friction stress. So these are all the things are playing important role. That's why we are getting a very low activation volume. Okay, so from this particular deposition, we could able to optimize the laser power and scan speed for this particular sample, and also so we understood that there is some kind of preferred structure is like preferred, not preferred, predominantly 001 texture is there in the building direction. That is mainly due to the thermal gradient, because layer by layer when we are going, the heat will keep on accumulate. That will create some kind of thermal gradient. So that's why it leads to the epidaxial grain growth mechanism. Okay. So also we did some nano notation. So we got this strain rate sensitivity and lower activation volume. So these are all this. So we got this reason is mainly due to this short range barriers, right? So that's what I told. So this is from the first study we got. Okay. So now the second study, what is our objective is we try to change this scan pattern. Okay, we try to rotate this scan pattern. Like in the previous case, the scan we not change the scan rotation. Like it is in the 0 degree, means same layer by layer. It will go in a similar orientation. It will deposit. But in this case, keep on this scan pattern will rotate. Okay, like for example, so we did it in a 3 different conditions. We have rotate the scan, that is called like interlayer scan rotation. So we use the 67 rotation and 90-degree rotation. Means after one deposition, suppose 90-degree rotation means second deposition it will be 90-degree, it will be rotated. So each deposition it will be 90-90, it will be keep on rotated. So in that sense, you may get this cooling rates, it will change. Okay, basically this thermal gradient that it won't affect. Main our objective is how we can reduce this epidaxial grain growth. Even the substructure also we observe this too much of epidaxial grain growth. So when we are doing this 0, 90 and 67, we understood that the middle is the 67-degree. Okay, the 67 is giving a very fine structure than 0 and 90-degree. We just we did multiple images, and then we tried to measure this substructure. We understood that the finer structure is we got it in the 67 degree, and also the epitaxial growth also it is depressed or it is reduced in the 67 degree scan rotation. Okay, so also if you see the EBST, like here we can understand the microstructure and texture. Already I told. So for first case, already I told 001 texture is very like preferred orientation is forming, but 67 and 90 is forming a very refined structure as compared to 0. 67 and 90 is having a very kind of very refined microstructure. Also the texture also quite different. Okay, there is no strong texture is forming, very different kind of 111 or 101 fiber components are we have found it. These are all the misorientations. Okay, the misorientation also less as compared to the 0 degree rotation. So already I told the cooling rates are much good. So that's why it is forming like the misorientation is reduced here. So also we did some phase analysis. In all cases, it is forming a FCC structure. There is no change in the any phase change. It is forming a single phase FCC. So also we did some kind of it's like automated ball indentation kind of test. Uh, Something like a harness only. So you can understand this how much maximum energy is absorbed in the particular sample. We can understand by using this ABI. So usually this 67 is giving a almost giving a similar kind of energy absorbed. Okay, as compared to like other orientation. So yes, 0 if you take, there is too much difference in the displacement. Okay, that's what we understood. And also if you take the mechanical properties, uh, for example, in the scanning direction and building direction, it is totally different. Okay, so in case of scanning direction, it is giving a better yield strength, that but ductility is very less. But in case of building direction, the ductility is much higher, uh, but strength is less. Okay, if you go for 67 and 90, almost all cases the strength is increasing. The 67 is giving a better like even 90 is giving 90 also giving better strength, but in case of isotropic property, the 67 is giving a better results. Okay, so we are getting a better results from the 67 sample. All cases it is showing a dimples. So dimple fracture structure, basically it is indicating that it is a FCC. Like usually this ductile samples will fail by this by using these dimples. Like dimple structure you will observe in the ductile fracture. Okay, so that's what we understood. So by using this different scan strategy, what we can understood is we could able to control the microstructure and texture both. This globular grains is totally it is reduced in the 67 and 67 degrees scan rotation, and also we could able to change the texture also. Like in B67 we observe the 111 101 fiber texture, or other fiber textures are there, but there is no strong cubic texture is not present in the 67 sample. So basically this 67 scan rotation is giving a better strength and ductility as compared to the other cases. Okay, that's what we understood. And in final case, we try to third case, we try to change this composition. We try to see this how this cobalt content is changing the cobalt content, how it is affecting this all this microstructure texture property in this laser additive sample. Okay, so because why we want to study this particular cobalt addition means, so usually when we are changing this cobalt, that will vary this stacking fault energy value of this particular sample. So when you are changing the stacking fault, probability of this twinning and some kind of phase transformation will be happen during the deformation. That's why the high probability of twinning and monocytic transformation is possible when you go with cobalt rich sample. That's why we try to increase this cobalt up to 60%. Okay, in case of ego atomic, it is 33%. but we want to go for 40, 50, 60. Okay. So when you are increasing this cobalt content, clearly you can see that there is complete transition in the particular this substructure. Like kind of when you increase to 60%, the substructure is totally it is the refined. We got it in few micrometers. So also when you are changing this, increasing this composition, there is other phases are coming like kind of the martensitic phases are evolved in this particular 50% and 60%, like up to 40% it is single phase FCC. When you go with 50 and 60, you can see the higher proportion of martensitic, like here this red color is showing a other two phase. Okay, so this also will enhance the strength in the particular mechanical properties, or if you are going for fatigue property, like so some of the optimized dual structure will give a better properties. So that's why we try to see this composition variation. Okay, so in case of 50, it is below 5%, the martensitic transformation is, but in case of 60, it is almost 55 to 50% martensitic transformation has happened already. So that's why here you could able to see a large amount of higher angle grain boundaries because of this transformation, because all are nucleated in this particular grain boundary. But here in first case there is in the boundary there is no nucleation of this martensitic transformation, but here again second 50% you can see certain areas having a martensitic transformation that is having these different colors you can see here. So also we this uh, third one is showing a misorientation plot. There we can understand that how it is strained or highly strained or not. Those misorientation also will tells us. Okay. So also we separate out this different phases and try to see each phases and how the texture is changing and what kind of texture is forming. All those texture study also we did it. Also we try to see the properties. So here basically when you increase this proportion, usually the strength is enhanced, but at the same time the ductility is went down. Basically the 33 is giving a better ductility with better strength. 40, if you take 40, the strength is really good as compared to ecoatomic, but the ductility is went down to 40%. Okay. Also 50 and 60, if you take, even in between the uh, uh, even it can't able to obtain the very higher strength, very less ductility itself, it got broken. The samples are broken. All the samples are mainly because of this transformation. Like quick transformation is basically it is dominating. Because of that, the samples are behave like a ductile material. Like here also you can see that how the transformation of this like factorography images, like after tensile test we did the imaging, like it is called like a factorography images there. Here we are not seeing about much dimple structure. Okay, like in the first case dimples are there, but if you come to the 50 or 60%, mostly it is having it doesn't have any kind of uh, like uh, uh, like ductile behavior, no dimples, right? Like kind of planar facets or ridges are there. So these are all basically it is indicating that it is having a brittle structure. So by using that compositional modification and also by using this advanced manufacturing technique, so we can combine this technique to we can improve the mechanical property with ease of fabrication, and there is no need of further post processing requirement. So that is the advantage of this compositional modification. Okay, so now I'm coming to this fourth study, laser shock pinning. Before going to the into that, so you should know what is laser shock pinning. I need to show certain image, then you can understand this how this laser pinning will work out. Okay, maybe, yeah, I hope it is there. Uh, this is basically the, so what is the basic phenomena will happen? Okay, like suppose the laser beam is bombarded over your particular sample, so that will give some kind of high energy plasma. Okay, this laser beam will give a high energy plasma that will be, when it is hitting with this or bombarded with this material, it will convert it into a very high energy shock wave. It will induce into the particular material. Because of that, it may refine the material, or it can change the any phase transformation also, it may happen. Also, mostly it will induce a microstructural refinement. So that is the main idea of doing a laser shock peening. Okay, there are some other methods also there. People will use this SMAT process. You can study about this mechanical agitation process. There they will use the steel, some of the steel balls to bombard over the surface. Then they will induce a shock wave. Like that, here we are using a laser beam, high energy plasma we are using. Then we are converting this high energy plasma into a shock wave. Then we are refining the structure. So for that purpose, here basically this India pulse laser is used here. Uh, by using this, we can automate this process also. Suppose if you have the CNC stage or XY stage, so you can move the sample with respect to XY direction, then layer by layer, like you can do a pinning. Okay, so that's what. So basically, to modify the surface property. Okay, so usually this powder based process, the surface roughness usually will be in the micro to nanometer to micrometer. Still, if you go for VAM and all, surface property will be little bit. The surface roughness will be much higher, like a few nanometer, few micrometers. Then you need to do some kind of machining process also. We have to do as a secondary process. Some cases, okay. Um, so here basically we did some different kind of short pinning. Hope before going to the result, maybe I should show what kind of mechanism will happen. Then you may uh, understand about this, how we can. Are you able to see this slide? Any of you please tell me. Uh,
Yes, sir, but it has to be in view mode, slide show mode.
okay, just few slides I have to show, like one or two slides. Uh, After that, I will switch it actually. So basically, this is the application of this pinning process. Okay. So for example, so here basically here no need to hold the sample under, like precisely we can do a treatment, and also the tooling cost is very less. Also, whatever the complex geometry, you can do a pinning. For example, here the connecting rod, they are doing this pinning process. Also this impeller blade, how they are doing this pinning process, you can see here. Okay, so basically when you are doing this pinning, this is the mechanism will happen. Okay, so that's what I try to say. So near to this near to the particular layers outside surface, I'm starting from the outside surface to inner core. So in the outside surface, so basically completely your microstructure will get refined. Here this basically this blue color lines are, call it like a mechanical tuning. Okay, mechanical tuning is happened, and some kind of T symbols are there, that is basically indicating a dislocation, like more dislocation, and your grain size is refined in the near to the outside surface. When you go inside, then keep on your tuning will decrease, and also the dislocation also it is started to decrease. At in the core structure only we have a few dislocation. Means along the depth we are generating a heterogeneous microstructure. Okay, just by inducing this shock wave, we are refining the refining the surface. Near to the surface level it will get refined, but if you go inside, it will be like very less. Okay, so that's why in that case, In the surface level, the hardness will be much higher, but if you go down, the surface, if you go inside the surface, then it will decrease. The hardness value may decrease. So also, so when you are doing this shock wave, so it will generate some kind of compressive residual stress. So this compressive residual stress is very really good for the some kind of pores are there that will get closed. Okay, pores or cracks are there automatically, that will get reduced or closed when you are inducing this laser shock wave. That is also good for the additive manufacture sample. Okay, so that's what people will go for the additive manufacturing process. Okay, now I'm coming to the slide again. So similar thing we have tried in our three component system. Okay, three component system. For example, you see here like almost when you are doing one shot of laser shock printing, there is no difference, no such difference. When you are going with two LSP, like some of the dots are there, that is basically a refined structure. But when you go to the third three LSP, 3 cycles of LSP, there is a large amount of low angle boundaries are formed. Means it is a large here large refinement and strain is formed. So because of that, we could able to get a different property out of it. Like you see here, like when you increase this LSP, keep on this uh, the strength is get enhanced. Okay, strength also enhanced and also ductility also enhanced after the 3 LSP for this particular sample. That's what we understood. So from this study, we understood that so at least 3 LSPs, 3 seconds of LSP is needed in order to change this particular property or surface of this particular alloy. So we could able to uh, like increase this ductility and also strength. Okay, so elongation is basically greatly it is increased. Okay, so also from the factography study we understood that all are forming a dimple structure, so the mode of failure is a ductile failure. Okay, so that's what we understood. So also I can show some kind of like some kind of post processing technique also. Means we did some kind of cryogenic treatment for the different hours in this particular sample. We try to see the if there is any change or not in the. This also will act as a microstructural refinement. So when we are treated cryogenic temperature, usually this also will induce a residual stress, and then you can increase this. You can increase the properties. So in that way, we did some different hours. We try to do this cryogenic treatment, and we try to see the properties, but we are not seeing much difference. But at least 20% enhance like in the yield strength. That's what we could able to see, but there is not much difference in the energy absorbed or elongation. Okay, so that's what we understood from this cryogenic study. So so overall, what we understood is uh, so what we understood is like initially when we are doing deposition, it is the grain structure is different and also it is forming a preferred kind of texture. But when we are changing to the scan strategy, it is giving a better results than as deposited sample. Like as compared to the 0 degree scan rotation, 67 and 90 is both are giving a better property, and 67 is but giving a better isotropy in case of strength and ductility. That's what we understood. And also when we are changing the composition modification, we got the different phases. That also we understood from this study. Also when we are changing the phase, only we can go up to 50%. Like only we can go up to 45%. Like when you crash the 45%, like the sample is becoming brittle. Okay, that's what we understood. Because of this too much transition, that also will act as a it leads to a crack. Also, from the laser shock peening study, we could able to understand that at least 3 LSP cycle is needed to improve the property. So we got after 3 LSP, we got a heterogeneous microstructure with enhanced strength. That also we got it. Cryogenic treatment, it doesn't give much difference in the result, but there is change in the yield strength and the enhance in the yield strength we observe. Residual stress also changed. That we are still we need to check it. So that's what we understood from this case study. So what we did from this powder based process. So now one more study also we did it, that is based on the wire arc additive manufacturing. Okay, so in case of wire arc additive manufacturing, what we did is we have taken this same three component we did it. So we have purchased this nichrome wire. Okay, nichrome means nickel might be something like 70 to 80%, and chromium is having 30%, and we mix with the pure cobalt wire. Okay, there are two wires together, we have mix it at the same point. Then after melting, we have deposited over the substrate. Then we try to see the this non-ecotomic cobalt chromium nickel, how it is behaving. So that is giving a better property than ecoatomic. So we could able to get better strength and ductility than ecoatomic that we got it in the VAM process. Okay. Still, we are something we are trying to optimize the process parameter. We have to do some kind of different current and different scan speed. We try to change it, and still we try to improve the properties. That is going on with the other student. So we are studying with the other student VAM process. Okay. So one more is coating. The coating also we are trying to see how this material is behaving. That also one of the student is studying. So, feature we have to do this high temperature and wear corrosion of this particular alloy. So with this, I hope you got some idea about like how you can use this advanced material for the advanced manufacturing. Means how we characterize this additively manufactured sample, how we change this microstructure, texture, and how it is affecting the properties. I hope you could able to understand about little bit about our research. Okay, these are all the people are involved. Mostly we did with certain collaboration, RR Gate, US Singapore, and some of the labs we did some characterization, IIT Bombay or IIT Hyderabad. So okay. So if there is any question, maybe I can go ahead. Yeah.
Any question from audience? Question from audience, you can unmute yourself.
Oh, sir, this is Willingri.
Yes, please.
Sir, for additive manufacturing, which process is better for biocomposite material manufacturing, sir? Which is very suitable for
Biocomposite, like
yes,
nowadays this fusion is they are doing fusion jetting. Many people, many like it based on your application, like what kind of structure you have to produce. See, nowadays many people are using this. So what kind of material you told? Hello?
sir, actually natural fiber plus biocomposite, like
Okay.
for research purpose, sir. So only
Yes. Okay. Yeah, that's what. Like initially, I told, na, like one or two types of this. Mainly, it is used for the polymer. Polymer based technique will you can use it actually.
okay, sir. Thank
Yeah.
you.
Any other questions?
Hello, sir.
Yes, sir.
Myself, Dr. Manish,
Yes, sir. Yeah.
located Jaipur. Sir, you have shown 3 years kind of strategy. where you was telling that 67 degrees scan is giving the better result, for that tell why.
Yeah,
So
not 7,
have
sir. Not 7, sir. 67.
67, 67, not 7, 67, that is. So have you tried any other scan?
No, no. Mostly people are trying this different. In case of scan strategy, they are trying this 67 and 90. So usually these are giving better property because when we are rotating a 67, like in order to make complete rotation, it will take like much time. So in order to come to this certain same level, if you want to come again, it will take much time. So in that sense, the cooling rate is better. So the you won't get this kind of heat accumulation, like thermal gradient effect. You won't get it. That's what making different in this 67-degree and 90 also. Like so when you go for 0-degree, like same direction when we are doing it, the thermal gradient is a main problem. Uh, so that's what people are trying to do this 67. Mostly it is giving a better result. Like you can check a research papers. People are trying this 67 or 90 mostly. Like these both are giving a better results.
So
Okay.
what was the 45 degrees, sir?
45, 45 means similar, like right. 45, 90, like almost a similar kind of result you will get.
Okay, thank you, sir. I
Yeah.
request one to share the slide with
Yes,
us.
yes, I can share the slides. No problem. Yeah. Yeah.
Sir, madam, shall we wind up the session, sir? Okay, thank you. Let me conclude the session. On behalf of our management, Director cum Principal and Department of Electrical and Electronics Engineering, I would like to thank our resource person, Dr. Dan Satyaraj sir, Associate Professor, Department of Mechanical Engineering, IIT Indore, for his informative presentation on advanced manufacturing technologies, especially laser directed energy deposition, laser near net shaping, advanced material and its compositions, additive manufacturing, and the research aspects in the advanced manufacturing help for the clear understanding in recent technologies. Thank you, sir. Thank you for your wonderful presentation.
Thank you, sir. Thank you very much. Yeah.
I would like to thank all.
So if there is any queries, you can mail me always.
Also, I would like to thank all the participants from various institutions for their active participation. Thank you all. So we will join by tomorrow evening at 6 p.m. for session 5. Thank you. Once again, thank you all.
Thank you, sir. Thank you. Yeah.